All right, let's just dive right in. Welcome to this explainer. Today, we're going to completely demystify that magic inside your modern computing devices. You know, we use them literally every single day, but so often, what goes on inside these sleek metal and glass boxes, it just feels like absolute wizardry. Well, my goal today is to break down all that crazy complexity into a beautifully structured, logical journey.
So I want to pose a question to you right off the bat. How does a machine made of nothing but wires and tiny switches actually think? We're going to look right past those glowing screens and beautiful interfaces to understand the exact physical path that data takes inside the hardware. And hey, by the time we're done, you're going to see that it's not magic at all. It's just a highly organized, incredibly fast system of pure logic.
Here's our step-by-step journey for today. First, we'll look at the blueprint. Second, input. Third, memory. Fourth, the CPU. Fifth, output. And finally, multitasking. All right, Section 1, the blueprint.
To really make sense of all these circuits, we're going to use a simple, unified analogy that'll guide us through this entire explainer. Just like the quote says, program execution can be likened directly to reading a book. Think about it for a second. When you read, you normally just go word by word, line by line, right? But sometimes you jump back to an earlier place, or maybe you skip chapters that just aren't relevant, or you even do some quick math in the margins. Well, a computer processing data is doing exactly this, just at speeds we can barely even comprehend.
So to read this metaphorical book, any general-purpose computer really relies on four main components. You've got the arithmetic logic unit, the control unit, memory, and input-output devices. These interconnected pieces, they're absolutely the core of any modern machine, and the whole concept goes all the way back to early computing designs. We're about to explore each one of these, step by step, to see exactly how they pull this off.
Moving on to Section 2, Input. Entering the data.
Let's crack open our book and look at input peripherals. Now you are definitely familiar with these. We're talking keyboards, mice, touchscreens, microphones, digital cameras. Their sole job in the grand architecture of a computer is simply translation. They take human actions, a keystroke, a finger swipe, a spoken word, a beam of light, and they translate those real-world signals into something the machine can actually read. And what exactly is it translating everything into? Well, binary data. The absolutely crucial point here is that once your text message or your voice recording gets inside the computer, it's really nothing but a series of tiny electrical circuits. Using positive logic representation, when a circuit is turned on, it represents a 1. When it's off, it represents a 0. That's it. That is the entire alphabet of our computer's book, just ones and zeros.
Section 3, memory, storing the pages.
Let's talk about the number 256. In pretty much all modern computers, memory is organized into groups of 8 bits, which we call a byte. Because each of those 8 switches can be either on or off, a single byte can hold exactly 256 different numerical values. Everything stored in a computer's memory, whether it's a letter in an email, a single pixel in a photo, or a really complex instruction, is just a series of these numbers sitting in numbered addresses waiting to be read.
And this brilliantly illustrates two main types of pages in our book. First, we have RAM, or random access memory. Think of this as a temporary workspace. The computer can read and write to it constantly, but the second you power down, boom, those pages are wiped completely blank. Then we have ROM, read-only memory. This is the permanent, unchangeable text. It comes preloaded with vital startup instructions, what we often call firmware, that the computer absolutely needs just to wake up.
But wait, there's a third, highly specialized type of memory called registers. Let's bring our analogy back for a second. If main memory, your RAM, is the entire book sitting over on your desk, registers are the immediate sentence you are currently holding in your head at this very second. They live directly inside the processor itself, and they are ridiculously fast. This ensures the computer doesn't have to keep walking back to the desk every single time it needs a crucial piece of data.
Section 4, the CPU, the master reader.
All right, now we are entering the true brain of the operation. The Central Processing Unit, or CPU, is exactly what it sounds like. Ever since the 1970s, it's typically been consolidated onto a single microprocessor chip. The CPU is the master reader of our story. It contains those super fast registers we just talked about, but it also packs two vital new components, the control unit and the ALU. Let's see how they work together.
The control unit is kind of like the eyes and the conductor of the computer. It operates in this really rhythmic mechanical loop. First, it uses something called the program counter to figure out exactly which page and line to read next. It grabs that instruction from memory, Second, it decodes that numerical code into actual hardware signals. Third, it increments that program counter so it knows exactly where to look next time. And finally, it executes the instruction, over and over again, millions of times a second.
So what happens when that instruction requires some heavy lifting? Well, that's when the control unit hands the data right over to the ALU, the arithmetic logic unit. If the control unit is the reader, the ALU is the part of the brain doing the complex math in the margins. It handles all the arithmetic, like addition and subtraction, and it processes Boolean logic, statements like and, or, XOR, and not. This is exactly what allows the computer to compare numbers and make actual decisions based on whether something is true or false.
Now remember that program counter we mentioned a minute ago, the bookmark keeping our place? Well, the ALU can actually change that bookmark. By executing what are called jump instructions, the computer can modify the program counter to skip entire sections of code or create loops that just repeat paragraphs until a specific condition is met. This flow of control is a real game changer. It's what allows a computer to perform incredibly complex tasks without needing a human to intervene at every single step. It literally skips chapters and rereads pages all on its own.
Section 5. Output. Delivering the results.
Okay, so the computer has processed the logic. What happens when it's finally ready to share the story? It sends the data back out through output peripherals. These devices do the exact reverse of our input tools. Think about a monitor, a printer, a loudspeaker. They take that processed binary logic, those millions of tiny electrical ones and zeros, and they translate them right back into human-accessible form. They're turning raw math into colors on a screen, ink on a page, or sound waves in the air.
And that brings us to Section 6, multitasking, the seamless symphony.
Now, modern machines don't just read one book at a time. They appear to read dozens of them simultaneously. But how do they actually do it? Well, it's through a really brilliant system of time sharing driven by something called an interrupt. You see, human input is incredibly slow compared to a CPU. While the computer is just sitting there waiting for you to type your next letter on the keyboard, it gets an interrupt signal. This basically tells the computer to stop its current task, save its bookmark, and quickly sneak over to process another program, like playing your music or downloading a file.
The real reason this all feels like pure magic comes down to one simple word: billions. A typical modern computer executes billions of instructions per second. It can switch between your web browser, your music player, and your text editor hundreds of times a second. It's moving its little bookmarks so incredibly fast that, to human perception, it looks perfectly simultaneous. But in reality, it's just reading one word at a time, brilliantly organized.
So, we've covered the core hardware that makes all of this possible, but I really want to leave you with the thought about where this is all heading. If reading basic binary instructions at billions of times a second can build the massive virtual worlds we use today, what happens when we shift from purely explicit programming to machine learning? What happens when neural networks allow these machines to adjust their own parameters and essentially learn to write their own stories? That is the threshold of artificial intelligence. It's a fascinating leap from the hardware we explored today, and honestly, a perfect place for us to wrap up. Thanks so much for joining me on this explainer. Keep questioning the magic and keep learning.